Section 8.1 is the average value theorem and accumulation of rate functions. We talked a little bit about rate functions back in chapter 4, so we're going to go back and talk a little bit more about them. But let's start first with the average value function. So there in your notes, in your book, there's just an introduction on how you find, on like what the average value function is and where it comes from and where the formula comes from. So let's run through this really quick. It says the average value of a function represents its average height. So when we think about its height, we're thinking about the y values. So the first thing says draw a horizontal line segment from A to B in the figure at the right, which would represent the average height of f of x on A to B. So if we're thinking of the heights are the y values. So, you know, those are all my y values as I trace across there. So what I want to do is draw a horizontal line. You guys go ahead and do this. Somewhere that I think represents, that probably should be a little bit higher, represents the average height of all those y values I just outlined in red. Let's say somewhere in there would represent that. It says find the area the rectangle formed. So we've got this rectangle now in blue. We want to find that area. So the area is equal to the width. So how far is it from here to here? Well, to find that, I would just take subtract my 2x. I'd go b minus a. So that width is b minus a times by the average height, right? This is b minus a. This is the average height right there, whatever that comes out to be. Well, if you think about this for a second, the area of that blue rectangle right there is actually going to be exactly the same as the area of that red, of that shaded area in red. Think about that for a second, see if that makes sense. If the height of that rectangle is the average height of all of the red figure, the width's the same on both of them, so their area is going to be the same. So what we're going to do now is just use that to discover the formula. Well, I know how to find the formula of the area that I just shaded in red. That's just the definite integral from a to b of f of x. And that's got to equal the width, which we already said was b minus a, times the height. Well, we're trying to find that average height. We're trying to find this right here. Like how high is that right there? Well, to solve for that, if I just divide by b minus a on both sides, I end up with a formula for finding the average height of a function, or the average value of a function, which is really just the height of that rectangle right there. Okay. So that brings us to our formula. So this is the average value formula. Remember, keep in mind, important things, is the average value formula is used to find the average height, or the average of the y values. What we're going to do is take the area of the region, which we find by taking the integral from a to b of f of x, and we divide it by the width, and what that gives us is the average height. And you can put the b minus a below the integral, or you can put it out in front like this, 1 over b minus a times the integral. That's up to you. For this to work, the function does have to be continuous. So if the function is not continuous, then you can't find the average height. Okay, so let's go through and do one of these problems. This one says find the average value of f of x equals x cubed minus x on the interval from 0 to 2 without using a calculator. Okay, so we're just going to use our formula. So our formula is the average value is 1 over b minus a, that'd be 2 minus 0, times the integral, the area of f of x, x cubed minus x, dx, and again I'm going from 0 to 2. That could also be written this way, right? Whichever you prefer, it doesn't matter if you want to, over 2, that's fine also. Okay, I'm just going to do it this way up here, so I'm going to start by finding this. So I'm going to have 1/2 times, and the integral would be x to the 4th over 4 minus x squared over 2, and we're evaluating it from 0 to 2. All right, so if we plug 2 in, I have 1/2 times, let's see, 2 to the 4th is 16 divided by 4 is 4, minus, plug 2 in there, 2 squared is 4, divided by 2 is 2, minus 1/2 times, if I plug 0 in, so end up with 0 minus 0, Let's simplify that. 4 minus 2 is 2. 2 times a half is 1. Half times 0 is 0. So it comes out to be 1. That is the average y value, or the average height of that function. So let's draw a picture and see if that fits. So I'm going from 0 to 2, between there, and we're saying the average height is 1. So if you look at that, that looks pretty good. You know, if I'm just guesstimating here, you know, I'm coming along this way. Those are all below 1. That part's above 1. I average them all out. It's going to come out to be 1 in between there. Hey, example 5 wants us to go back and do that same, go back to that same problem, but it says use your calculator to find the value of c in the interval from 0 to 2, where f of c equals the average value. So if I go back to here, what it wants us to find is find the x value right here, where the actual value of the function, the value on the green graph, right, the value of the function is equal to the average value, is equal to 1. So what I'm really doing is I want to put 1 in for y and find out for what x value does my function equal that actual average. So it's going to look like this. I'm going to go 1 equals x cubed minus x. And what I'm really looking for is what is that x value right there. All right, so we're going to use a calculator for this one. So minus the 1 over, so you get 0 equals x cubed minus x minus 1. And then we know how to do this. We're going to take this and graph it. So we're going to graph y equals x cubed minus x minus 1 and find its zeros, and that would be the answer. When you do that, remember, it may have more than one 0. We're only looking for the one that's between 0 and 2. And you can have multiple times where you can have multiple x values where the actual value of the function equals the average on some graphs. This one, though, we can see the graph. It only has 1 point, but there could be more, I mean, with other functions. Okay, so go ahead. You guys can go ahead and solve that. If I remember right, it comes out to be 1.3 something, something, something. But anyway, go ahead and solve that. Make sure you get that answer. Okay, the second half of the graph is dealing with rate graphs. So let's go ahead and we've actually done we've done part of these problems before. We're just going to add a little bit to it. So you have this is accumulation of rate graphs. It says in lesson 4.1 you interpreted rate function models. We can now revisit the topic and include the concept of accumulation. So that will be the new part. All right, so this one says the graph at the right models the rainfall in inches per hour from midnight to 6 a.m. During a tropical rainstorm. So just be careful. This doesn't tell us how much rain fell. This tells me the rate, right? The rate that the rain fell, and it's in inches per hour. I want you to pause the video and do 6 through 9. All 6 through 9, we've done each of those before on that lesson 4.1, chapter 4, way back then. So try those on your own really quick. Get your answers. So pause the video and do that. And when you come back, we'll go through it together. And then we'll finish those last two and talk about this idea of accumulation. All right, so hopefully you've worked down through those. Number 6 says write a complete sentence to explain point A on the graph represents. Point A is right here. So that means right here at, see this is hours since midnight, so at 3 a.m. the rate of rain was, this is the rate over here, right? If I come this way. So at 3 a.m. the rate of rainfall was 1 inch per hour. Something similar to that. 7 says, what is the slope of the graph between B and C? Hey, be really careful when you're finding slope. Sometimes we want to say that's down 4, right? We're going from 1 to 0. It's down 1, and it's over 1. So it's -1 would be my slope. 8 says, write a complete sentence to explain the meaning of your answer to example 7. So if this is the rate graph, if we take the derivative, it's the rate of change of the rate. So it's the rate of change of the rate. So we could say the rate of change of the rate was changing by a -1 inches per hour per hour. Or we could say inches per hour squared. You could write that either way. So the inches per hour squared. What that really means is the rate that the rain was falling was slowing down. And the rate that it was slowing down by was 1 inch per hour per hour. Okay, number 9, we want to find the definite integral from 3 to 5 of r of t. So we're just looking for the area under the curve. And we can find that from 3 to 5, right? Because we could split this into just a rectangle and a triangle. So again, just be careful with the area. This is 1 by 1, so that would be 1. This is 1 by 1, but it's a triangle, so half of that would be a half. And so I should change that color. That green's terrible, isn't it? Sorry about that. If I add those together, I get 1.5 or 1.5. Okay, this is the new part. We're going to write a sentence now explaining the meaning of that answer. And this is the part that we did not do before. So this will be new for us. So when you have a rate function and you integrate it, what it gives you is an accumulated amount over that time. So what I mean by, right, we found the integral from 3 to 5. We found that area under the curve right there. That area gives me an accumulated value. In this case, we're talking about the graph is the rate the rain is falling. So when I integrate it, it actually tells me how much rain fell. So at number 10, we would say this. I would say from 3 a.m. to 5 a.m., 1.5 inches of rain fell, a total of 1.5 inches of rain. Hopefully that makes sense to us. So when you integrate a rate graph, it gives you an accumulated amount. So if I had a rate graph that was going miles per hour, and I integrated, or a function that was giving me the rate miles per hour, if I integrate it would tell me the total miles traveled. Okay, so when you integrate a rate function, you can do that with a graph, or they could give you the function. When we integrate that, it'll give us an accumulated value. All right, so number 11 says we want to approximate the definite integral from 0 to 6 using geometric regions, show your computations. So if I'm going to do that, like I already know, I guess, this part over here I already know. I want to go from 0 to 6. Over here there's no, so I don't have to worry about that. We already know this one is 1.5. So to approximate the rest of that, we could do that a couple different ways. I think I'm just going to do a triangle just to make it fast. And that triangle does a pretty good job, right? I have some region that's above the triangle, but I also have some region that's below the triangle. So that is 3 by 1 divided by 2. So that would be 3 halves, or let's just call it, let's put root as a decimal, would be 1.5. So altogether, if I add all that up, it's approximately 3. Okay, go down to the next part. Write a complete sentence explaining the meaning of your answer of example 11. I want you to pause this one. I want you to write what that answer represents. Write a sentence and then come back and we'll talk about it together. Okay, so we are integrating a rate graph. That gives me accumulated value. So in this example, what are we accumulating? Well, we're accumulating the rain. Like it's the rate the rain fell. So when I integrate it, it gives me a total amount of rain. So number 12, I'd say, write a complete sentence. It would be from midnight to 6 a.m., a total of, or approximately 3 inches of rain fell. And I'd say approximate, right, because we didn't find the exact value, we just approximated it. So most of that we know, like we already know, we've already talked about rate graphs and we've answered questions from rate graphs. We're just adding this little piece to it where if we integrate it, which find the area to the curve, or integrate a function, a rate function, it's going to give us a total accumulated amount. And that's it for this assignment. So the two things you're going to be practicing, right, are finding the average value of a function, and the second part is finding, using rate functions to find accumulated values. Let me know if you have questions. Thanks, guys.